Hello everyone. In this session, I will go over the first step of implementing our model in Python, which is data pre-processing. So this is our data set in CSV file, and I will be doing the XGBoost regression first. So I will go ahead and open the Google Collaboratory. First of all, we'll have to implement the necessary libraries. So I'll annotate as so. These are the libraries we will be needing for our Python model, and in the next cell we will have to import our dataset. Before that, we will have to first upload our dataset into this folder. So I'm giving it some time to initialize, and then I'll just drag my dataset and paste it here. The name is mldataset.csv, so it's there, and we'll have to define it in our code like this. So in the next line, we'll check whether that check the status of our dataset. So print set dataset. So we'll have to run this cell first. So it is done running, so that we can run the second cell. This is currently what is uploaded in the variable dataset. So there is our observer, thickness, defect, donor density, PCE, and there are some unusual rows columns at the end. We have three more columns which all have nan values. Nan means not a number. So these columns are unnecessary, which somehow got into our data set. So we have to get rid of them first. So to get rid of them, we can write this line. So and dataset.drop na. X is one means the column, and how means all the columns that has the nan values in them. So we'll run it again and print our dataset later to check whether it worked or not. So as you can see, we got rid of the unnecessary columns. So now it looks more correct. So now we have to split our training, our independent variable vectors that are the first first four columns, and the output parameter is PCE. So we have to separate our input parameters and output parameters. So to separate, I'll have to use this line. So all the input parameters will be stored in the X variable, and this first column means that take all the rows available in our dataset. That's why we did not specify the before and the rows limit. And this first empty space before column means we will start taking all the columns until we have our last column. It means that we'll take all the columns except the last one. So we will take absorber thickness, defect, and donor density, but we will ignore the PCE into our X. So next we'll have to take the PCE as Y variable. So this means that take all the rows, but only take the last column. The negative one will without any column will mean that we will only take the PCE column. So I will run it again. We can get rid of this testing. And to check whether our x and y are correct, we can just test it as print x. So the first one is absorber, thickness, defect, and donor. So we don't have PCE here. And if we check for y, you can see that it's an array of all the PCs only. So our separation was successful. So we can go ahead and get rid of this cell. So we have successfully imported our dataset. And now we will have to handle any missing data that might be present in our dataset. So, and I'll just paste the code first and explain it. So missing values can be handled in several ways. For sensitive dataset, you can just delete the rows that have missing values, and if you have a large amount of data, this will not probably not cause any significant um, effect in your model. But you can also replace the missing values with different strategies such as mean, median, mode, etc. In our case, I have double checked our dataset before importing it in Python, and I've seen that there was no missing values. This is just for demonstration purpose. So I have to import an object called simple imputer from the scikit-learn library, and I have been told that I will replace the nan values with the mean of that column. And which rows should I apply these strategies to? Well, I will go from row 1 to row 4. Now this is something you have to understand. The one means actually the second column. Our first column is the names of the observer. So there are no values actually. So if we inserted 0 here, that would have meant the first column. Since we have inserted 1, it will actually consider from the second column. And we have inserted 4 here. So let me just print the data set again. So this is the 0th column and this is the first column. So we will take the first column, but we'll take the first, second, and third. So if we stop after the third column, so we'll have to specify write 4 here. This is called a non-inclusive method. So if you write 4 here, it will take up to up to 3 columns, and if we write 5 here, it would have taken up to 4th column. So if we want to take the nth column, we'll have to insert n plus 1 here. So that is the strategy here. So we have handled the missing data, and I'm going to run the cell now. Now we have to do something about our first column. So we have to encode these names into some values, and I'm going to go ahead and do that. So these rows with names in them are called categorical data. So these are categorical data, so we have to encode them before going any further. So encoding categorical data, and we have to import an object called level encoder, and we will initialize level encoder. And we'll fit and transform only the first column. That means the 0th column of x. So this just means that since we will be replacing the names with 0, 1, 2, 3, etc., I wanted to save their name corresponding to their labels for any future possible uses as a dictionary. So this line just does that. And I want to see which level went to which name. So I'll go ahead and run this now. So cesium lead bromide was assigned to 0, cesium lead iodide was assigned to 1, and so on. Now I'll go ahead and print the X again to see if the label encoder was actually applied in our independent variables. So as you can see, the first column was encoded as 120123s with these, so it was successful, and the rest of the columns remain the same. So that's it for this video. I will be completing our model in the next one.